Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, and here we have our first speaker. We're going to learn about how to detect three-variable interactions. The authors have already worked on two-variable interactions, now three. Maybe this talk, there's a very big difference from 2 to 3. And hopefully we'll also get promise of how we can do 4 and even more. The talk will be given by Dino Sedinovic, Arthur Gretton, and Richard Bergsma are co-authors. So it's from Gatsby in the UK and London School of Economics.
Thank you. So I will be talking about a nonparametric hypothesis test for three-variable interaction. Okay. Which is based on embeddings of probability measures into reproducing kernel Hilbert spaces. So let us start with a simple motivating problem. Say that we're interested in detecting V-structures in a directed graphical model where pairwise associations between individual random variables are very weak and very difficult to detect. In other words, dependence of Z on X and Y jointly is much stronger than on X and Y individually. For an illustrative example of that, you can consider the case where X is whether you put sugar in your coffee, Y is whether you've stirred it up, and Z is the sweetness of the coffee. So individually weak effect, jointly strong effect. And you can even argue that Y is independent of Z in this case. It is also straightforward to construct an extreme example where all three variables are pairwise independent, but there is joint dependence, and you can argue there is a V structure like this. It suffices to consider X and Y being standard normal, and the sign of Z depending on the sign of the product of X and Y. So this is the continuous analogon of the XOR in the binary case, if you will. So if you look at the scatter plots, it's clear that X is independent of Y, Y is independent of Z, X is independent of Z, but there is joint dependence. So how do we go about detecting these structures like this, where we don't have pairwise dependence? That's the question that we're trying to answer. But before we get in there, we will first review how to do a standard pairwise independence test. So this has been known for a while. For a couple of years now, based on embeddings of probability measures into reproducing kernel Hilbert spaces. So let's say that we have a data that looks something like this. So we're interested in a fully non-parametric framework. So our data may lie in a non-Euclidean structure domain. So say that X is paragraphs of English text, Y's are paragraphs of French text. And we are interested in detecting dependence between them. Perhaps we want to test the hypothesis that one is translation of the other. We're not interested in the translation problem, that's too difficult. We just want to detect whether in the pairing there is some information here. Okay. So what is an intuitive way to approach this problem? So we could pick a similarity measure on paragraphs of English text, say K, form a corresponding similarity gram matrix, do the same for French. And then we can consider what similarity between these two matrices means. It means that when we have an entry in a matrix, similarity between two paragraphs of English text, and this is large, then the corresponding similarity between paragraphs of French texts also tends to be large. So this is a good evidence against the null hypothesis that these are two independent data sets. So it's quite intuitive to consider just an inner product between these two matrices, and that is an intuitive dependence measure. So these kernel gram matrices are just centered by a standard matrix H. This means that we're just removing the mean from each of the columns. Inner product is just the entry-wise product of these two centered matrices, and then we just compute the sum of all elements. So this is this notation ++. So that's an intuitive dependence measure. Let us see where it arises from. So this is just a standard kernel trick feature map formalism. So we replace our explicit feature map, phi1 up to phi s of an individual data point z, with an abstract feature map that lies in a Hilbert space, k.z. We don't really care about the explicit coordinates of this k dot z. Indeed, in many cases, this is an infinitely dimensional object. Only thing we care about is that we can easily compute inner products between individual features. That's just the kernel function. So embedding of a probability measure is just one step further. Rather than considering a feature of an individual data point, we consider a feature of a distribution. So embedding of a probability measure P, denote the mu Kp, is just this expectation of the canonical feature, where expectation is taken over a Hilbert space. So again, we just have some representation of a probability measure, which replaces, say, representation in terms of moments. It can be infinitely dimensional as well. We don't care about the explicit coordinates of the representation. Only thing we care about is that we can easily estimate inner products between individual embeddings. This boils down to just an expectation of the kernel function with respect to these two probability measures, P and Q. Okay, so now that we have an embedding of a probability measure, it's natural to consider a notion of distance between probability measures that's based on these embeddings. So we say that distance between P and Q is just Hilbert space distance of their embeddings. This is called maximum mean discrepancy in the literature. For a broad family of kernels K, this embedding is injective, meaning that MMD is a metric on probability measures. And for a slightly stronger condition that is called integrally strict positive definiteness, we have this embedding injective on all sign measures. Most of the kernels that we know and love are integrally strictly positive definite. Okay, so now we have a notion of distance between probability measures. So what does that have to do with dependence? Well, then it's very easy to construct a dependence measure by just looking at the Hilbert space distance between the embeddings of the joint distribution and the embedding of the product of the marginals. So this is known under the name of Hilbert-Schmidt independence criterion. So here we're working with the product space. So we need a kernel on the product space. This is denoted kappa. We can use any kernel on the product space that we want, but one choice is just to take the product of kernels on the individual spaces, K and L. And when we do that and compute the empirical version of this quantity, we get exactly what we started with. So this is precisely just the inner product of centered kernel matrices that's normalized in a particular way. Now we can proceed with creating tests using this statistic, and this results in very powerful framework of independence testing that generalizes other approaches that appear in the literature, including distance covariance in by Sekeli and Coauthors in the statistics literature. Okay, so that is our dependence measure, Hilbert-Schmidt independence criteria. So let's go back to our original problem of V-structure discovery. We know now how to test for pairwise independence. We've known for a couple of years. So let's assume that we've established for this problem already that X is independent of Y. Then we can proceed with detecting this V-structure by posing a conditional independence test, whether X is independent of Y conditionally on Z. So this has been done by Zhang and Coauthors in 2011 by extending the notion of H-sig. Or we can proceed in a different way and consider a factorization test, where the null hypothesis is that joint distribution of these three objects factorizes in any way. So this is now a multiple hypothesis testing framework. Each of these individual tests is just a standard kernel-based test because we can consider X and Y just to be a single object. So in a multiple hypothesis testing framework, we have to apply Holm-Bonferroni correction on the p-values of individual tests. And so let's just do that on our standard problem, where we have pairwise independence and joint dependence. To make the problem more interesting, we're going to append a bunch of dimensions of noise here. So we just have p-1 independent dimensions, so there is dependence that is only joint but not pairwise in the single dimension. So when we apply those two approaches, we get something like this. For dimensions 1 and 2, we're doing all right, but the type 2 error increases quite rapidly as the dimension increases. And that's somehow to be expected because we're dealing with quite a difficult problem. This is with 500 samples and with median bandwidth Gaussian kernels. So can we do better? That's the question. And the answer is that we can by tackling this factorization hypothesis directly, by looking at the quantities that directly capture whether joint distribution factorizes. So this quantity is known under the name of Lancaster interaction. It's been studied in the 60s by Bahadur and Lancaster. So interaction measure of a joint vector x1 up to xd is a sign measure delta p that vanishes whenever I can factorize joint distribution in any way as a product of marginals. So x1, xd here need not be scalar variables. They could be random vectors themselves. The difference is just that we consider them as d different objects. So what are these interaction measures? For d equals 2, it's straightforward to see that this is just the difference between the joint and the product of the marginals. There is just one way in which joint can factorize. But for d equals 3, we get something like this. So this captures all the possible different factorizations of the joint of 3 random variables. So this is pictorial representation. And to convince you that this is a correct interaction measure, i.e. that it vanishes whenever joint distribution factorizes, say that we have the factorization in red. Then pxyz breaks down as pxpyz. But pxz also factorizes and pxy also factorizes, so blue terms also cancel out. So we get that Lancaster interaction vanishes. Okay, so this is just some sign measure on the product space. We know how to embed probability measures and sign measures into a reproducing kernel Hilbert space, so we just do that. So we construct a test which estimates the Hilbert space norm of the embedding of the Lancaster interaction measure. Kernel kappa on the product space now is just the product of 3 kernels on the individual domains. So we have just this Hilbert space norm squared. This breaks down as sum of various inner products between embeddings we know how to estimate. So we do, and we get something like this. So each of these v-statistic estimators of inner products just depend on the kernel matrices, individual 3 kernel matrices. And you see that there is some interesting structure in there. There are entry-wise products and there are matrix products as well. And we get just the sum of all elements of a particular matrix at the end. Now, when we take these terms all together and consider what the Lancaster interaction statistic is, we get something that looks like this, very simple. So the whole thing collapses just to a simple expression, which is just a 3-way entry-wise product between 3 centered kernel matrices. So an incredibly easy quantity to compute. And this is not a coincidence, because what we can view the embedding of the Lancaster interaction measure as an empirical joint central moment in the feature space. And this precisely captures this kind of quantity. Okay, so we just use now this as a statistic rather than doing 3 individual tests. And we get much improved type 2 error in our case, where we have pairwise independence but joint dependence. So even for the Lancaster interaction test, we have to apply a Holmbohm-Ferroni correction, because we are still testing 3 hypotheses. We just happen to be using the same statistic. So that was the example where we had pairwise independence but joint dependence. We can also consider an example that looks something like this. So here we have that z depends on x and depends on y as well, but the joint dependence on the pair is stronger than on x and y individually. Okay, so we look also at the comparison between the conditional independence test, standard 2-variable tests, and the test based on Lancaster interaction in this case as well. And we again get significantly improved type 2 error, especially in high dimensions. So you will notice that the gap between the standard 2-variable tests and the Lancaster interaction test closes in this case. And this is to be expected, because there is dependence of z on x and y individually as well. So two variable standard-based tests will also have improved power in this case. Okay. So now a natural question arises: is what happens when we go beyond 3? The answer isn't as satisfying as what we had in the case d equals 3 actually. The reason is that the interaction measure that was constructed by Lancaster does not actually capture all the possible factorizations in the cases d greater than or equal to 4. This was noticed and corrected by Strydberg in 1990. This is the correct Strydberg interaction measure. And you see what we have here is a summation over all partitions over a set of the elements. J pi p is here just a factorized measure that corresponds to particular partition. The number of partitions increases quite rapidly. So here's 52 for d equals 5, and here's how they grow up. They grow up quite quickly. So we can hope to be able to pose a test only if this expression collapses, just in the case of Lancaster interaction measure, but it doesn't, because the expression collapses only when we consider joint central moments. This is captured by Lancaster interaction construction, whereas this corrected version of interaction measure actually corresponds to joint cumulants. And joint cumulants and joint central moments only coincide when d equals 2 and d equals 3. For d greater than or equal to 4, joint cumulants are just some other polynomials, and we don't really have a collapsed expression. So while in principle we can go ahead, have that huge table and compute all the v-statistic estimators of inner products, it becomes computationally intensive quite rapidly. Okay, so just to summarize the talk, so we introduced a non-parametric test for 3-variable interaction and for total independence. Total independence is discussed in the paper. I didn't really have time to discuss it here. This is just another straightforward modification of the test. As a methodology, we used embeddings of sign measures into reproducing kernel Hilbert spaces. All the test statistics that we derive are simple and easy to compute. Corresponding permutation tests are straightforward to construct. They significantly outperform standard 2-variable based tests on V structures with weak pairwise interactions. For a very broad family of kernels, integrally strictly positive definite, we are guaranteed to detect with sufficient number of samples all forms of Lancaster 3-variable interaction, because embedding of sign measures is injective. And thank you very much for your attention. Our poster is S6.
Thank you so much. I see there's room also for talks for the next coming years when we have to go to 4 and above that. So there's time for a question or two. David?
So is there some notion of a strongest test? So is the Lancaster test known to be best in any quantifiable way?
That's definitely an interesting question, but we haven't done any comparison in that sense.
Any other questions? Okay, then let's thank the speaker again. If there's so by the way, now you're packing up. This was all done in synthetic data. Do you also have experiments for real data?
So we have done some initial tests on some genomics data where you have that gene expression of 2 genes actually has a switching property when you consider conditioning on the 3rd gene. And while definitely it's interesting to also be able to detect 3-variable interaction in this case, this is a data set where it is also easy to detect 2-variable interactions. And I think where our test can be really useful is in the cases where pairwise interactions are very difficult to detect. And this is something that we haven't really explored yet, but it's definitely part of the ongoing work of how to find these kind of cases for in real-world data sets.
Okay, good luck.
Thanks.
And the next talk, do we have a speaker? Okay. So in the next talk, we are going to move into a machine learning framework for synchronous parameter sharing, where you parallelize your computation, and the single worker may get a stale version of the parameters, but as far as I can see, there's a guarantee that it's not more than a certain amount stale when you get it, and we are going to get a rigorous treatment of the problem once the the whole talk comes up. The talk will be given by Chijung Ho? Jirong Ho, sorry. And it is work from Carnegie Mellon University.
All right, so good morning everyone, and thank you for having me up here to talk. My name is Chirong, and I'm going to talk to you about more effective distributed ML via Stale Synchronous Parallel parameter server. The motivation here is that we're trying to take a single machine iterative parallel ML algorithm from one machine to many. That's the distributed setting. And normally, in your algorithm, you have these critical update steps that are executed on one machine in parallel over many threads. The worker threads share these global model parameters theta via RAM. Now, we want to scale this up to a large distributed setting. So we now have to share these parameters over the network. That's synchronization. At first glance, it seems like a simple task. There are many distributed tools available, so we can just pick one and go, right? Well, it turns out it's not quite that easy. So there's two main distributed challenges. The first one being that networks are slow, far slower than the CPU to RAM interface. The second issue is that just because you spec out your machines identically doesn't mean they'll perform equally in practice. In fact, that's rarely the case. So let me explain what I mean by these. Networks are slow in the sense that they have low bandwidth. Low bandwidth, CPU to RAM is about 20 gigabytes per second. Over the network, it's between 0.1 to 1 gigabytes per second. That means you can transmit fewer parameters per second over the network. Furthermore, there's high latency or messaging time, somewhere in the order of 100 to 1,000 times longer, waiting for stuff to go over the network. And that means you wait much longer to receive parameters. The thing is that parallel ML requires frequent synchronization. You tend to have to exchange between 10,000 to 1 million scalars per second per thread in the single machine setting. If the parameters are not shared quickly enough, you get a communications bottleneck. And this is a significant bottleneck over a network. To illustrate this point, if you try to run a latent Dirichlet allocation topic modeling Gibbs sampler on 32 machines using the bulk synchronous parallel synchronization model, you'll find that you spend 6 times as much time waiting on the network as you do actually performing useful computational work. In other words, you're wasting most of your processor cycles. And that's for a clean setting with full control of the machines and full network capacity. In a real production cluster or research cluster, there are many other users, and you'll have even worse network compute ratio because you have to share it with them. The other reason is that machines don't perform equally, even when configured identically. There's a variety of reasons. Vibrating hard drives can slow down disk performance. Background programs are usually running in a large cluster. Other users might be using it, or you might be part of a VM or cloud service like Amazon EC2. The consequence is that you get these occasional random slowdowns in different machines, and I'll talk about how these harm distributed performance later. As a consequence, scaling up ML is a hard problem. Going from 1 to n machines rarely yields an n-fold speedup if you do it naively. That's because you get slower convergence due to machine slowdowns and network bottlenecks. And if you're not careful, you can do even worse than a single machine. You can diverge due to all these accumulated errors from the slowdowns. So there's a lot of literature on general-purpose distributed scalable ML, roughly divided into more theory-oriented work and more systems-oriented work. On the theory side, we focus more on algorithm correctness and convergence. On the systems side, it's more about maintaining that high iteration throughput by taking care of systems issues. On the theory side, there is sometimes a tendency to oversimplify systems issues. We might assume that the machines all perform consistently and equally, or we might need a lot of synchronization. In some cases, there are methods that just assume let's try not to communicate at all. But there really is a middle ground that we want to exploit. Then on the system side, they may oversimplify the ML issue, such as assuming algorithms just work in the distributed setting without proof. And in a lot of cases, you have to convert the program into a new programming model, which may be a non-trivial effort. Can we take both sides into account? So we advocate a middle-of-the-road approach. We want ML algorithms to converge quickly under imperfect systems conditions, the slow network performance and the random machine slowdowns that I've been talking about. The point being that parameters are not going to be communicated consistently under the setting. Existing distributed ML work mostly uses one of two communication models, the bulk synchronous parallel model and the asynchronous model. Before I talk about stale synchronous parallel, I'd like you all to understand the pros and cons of BSP and async. In the bulk synchronous parallel model, every worker thread on the cluster will synchronize or wait for each other at the end of every iteration. That's denoted by the red synchronization barrier in this diagram. Threads are always on the same iteration number, and parameters are read and updated only at the synchronization barrier. This is the ideal picture. This is what happens in practice. Because machines perform unequally, they take different amount of times to complete their iterations. The fast ones have the short arrows, the slow ones have the long arrows. And that's also because algorithmic workload might sometimes be imbalanced, which further complicates the problem. So, threads wait for each other. They spend a lot of time waiting for each other, in fact. Furthermore, the end of iteration synchronization gets longer with larger clusters due to the slow network. You're trying to communicate all those parameters right at the end, and so you've got a traffic jam. All that white space and all that red space is wasted computing time. In the asynchronous setting, we're going to say threads can proceed to the next iteration without waiting. So in general, they're not going to be on the same iteration number. The parameters can be read and updated any time, so that sort of removes the synchronization barrier bottleneck. What happens when a machine suddenly slows down? One thread will take longer to complete its iteration while the others are all speeding ahead. That causes an iteration difference between threads that leads to error in the parameter synchronization. In the worst case, on a large cluster, you can have an arbitrarily large slowdown. Machines may become inaccessible for an extended period. This is a common observation on a cloud network like Amazon EC2, where your machine might go off the network for a few minutes at a time. In that case, the error becomes unbounded because the iteration difference between that one thread and everybody else is growing rapidly. What we really want is a form of partial synchronicity. We want to spread the network comms evenly, and we don't sync unless needed. Threads usually shouldn't have to wait, but we can't allow them to drift too far apart. The other thing we want is a form of what I call straggler tolerance. The slow threads must somehow catch up to stop wasting everyone else's time. The question is there a middle ground between the BSP and asynchronous models of communication? That middle ground ideally should look something like this. When a thread is taking too long to complete the iteration, we're going to stop and say all of you have to sync up. And after that, we need to make that thread catch up somehow. It needs to process its iterations faster. How do we realize this? We introduce a system called Stale Synchronous Parallel, a model of synchronization. In this diagram, note that the x-axis is now iteration count and not time. The idea is that we allow the threads to usually run at their own pace, but we restrict that the fastest and slowest threads cannot drift more than s iterations apart. The threads cache local or stale versions of the parameters, and they read them whenever the model allows it. This is to reduce network syncing. A thread at iteration t under this model will see all parameter updates made before iteration t minus s. The protocol is simple. You check your cache first. If it's fresh enough, you use that value. If it's too old, you fetch the latest version from the network and incur some network cost. As a consequence of this protocol, fast threads have to read every network iteration because the slowest thread is going to force them to read every iteration. However, the slow threads only have to check once every s iterations. They make fewer network accesses, and so they catch up naturally. Thus, SSP provides a best of both worlds situation. It combines the best properties of BSP and async. It has BSP-like convergence guarantees, because the threads cannot drift more than s iterations apart, and every thread sees all updates before iteration t minus s. There's bounded error. It is asynchronous-like speed, because most of the time, threads usually don't wait unless there's too much drift. And slower threads can read from the network less often, so they catch up naturally to the faster threads. More importantly, SSP is a spectrum of choices. You can be fully synchronous. If you set s equals 0, you recover the bulk synchronous parallel model. Or if you push it to infinity, you get very, very asynchronous behavior. We advocate taking the middle ground to enjoy the benefits of both. Now, why does SSP converge? Instead of seeing the true parameter x, SSP sees some x stale, which is the true parameter plus some error incurred by all the stale reads. In SSP, the error caused by this staleness is bounded, and over many iterations, the average error will go to 0. Intuitively, you can think of SSP as approximating some sort of sequential execution. See the red line there? That's when I've ordered the updates in a certain order. We're going to compare this order, this ideal sequential order, to the actual update order, which is actually given by the white bars. Because of the staleness window, when you get to the point where you need to update the dotted black box, you may lose some iterations because some threads have not given you the information you need to proceed with that update in the correct sense. In this case, that's the blue box. You may also gain extra updates because some people are ahead of you, so they provide you these extra updates that weren't part of the original sequential order. Those are the orange boxes. So the total error in the system is the blue boxes plus the orange boxes. But that's upper bounded by the width of the two green windows. So that's the intuition in which SSP bounds the numeric error and thus bounds the error in the parameters. It's a partial but bounded loss of serializability. So more formally, if we assume that we are trying to optimize a convex function, which is L Lipschitz, its gradient is bounded, and there's a problem diameter is bounded as well, under staleness setting S and with p threads across all distributed machines. SSP then converges at a particular rate, where t is the number of iterations, but the main takeaway from this result is that the right-hand side bound contains both the arguments of the function, L and F, as well as arguments of the system, S and P. There's an interaction between this theory and system's parameters. So, SSP solves the distributed ML challenge by providing a synchronization model for fast and correct distributed ML. It reduces network traffic by caching local parameters whenever possible and addresses slow network and occasional machine slowdown problems. So how do we actually use this? We implement SSP as something called a parameter server. We call it SSPTable, which provides all machines with convenient access to global model parameters. It can be run on multiple machines to reduce the load per machine, and it allows easy conversion of single machine parallel algorithms into distributed ones using a particular style programming called distributed shared memory. If you look at the example on the bottom right, if that's your critical step, you replace all the array accessors Y with calls to the parameter server. The idea is to keep the program looking very much like a single machine program, but you get basically parallelization with minimal effort, distributed parallelization, that is. You don't need to do complicated message passing. And in terms of interface, it just has 3 commands. You don't have message passing, you don't have barriers, you don't have locks. You just read, you increment, and you advance to the next iteration. More concretely, if we're trying to make an application distributed, if it's a topic modeling MCMC algorithm, we would put the topic word table in the parameter server SSPTable. If it's matrix factorization, say using stochastic gradient descent, we'd put the factor matrices in. If we're doing LASSO regression, which is a coordinate descent algorithm, we'd put the coefficients beta inside. More generally, SSP supports generic classes of algorithms with these models as examples. Returning to this slide, I want to show you that SSP uses networks efficiently. On the left, we had BSP, and as we increase the staleness, the network waiting time drops relative to the compute time. At some point, we sort of hit a balance point where it's about roughly equal, and then we get diminishing returns as we increase staleness. But this is basically how SSP realizes speedups. We decrease that network bottleneck. In terms of convergence results, this is the LDA example on the New York Times dataset on 32 machines with 256 cores. Now, bulk synchronous parallel has strong convergence guarantees, but is slow in practice because of all the stragglers and slowdowns. Asynchronous is fast, but has weak convergence guarantees. If you let that curve go all the way to the end, it actually starts to oscillate. SSP is both fast and has convergence guarantees. There is a quality versus quantity trade-off when you use a system like SSP. I've shown that the network waiting time decreases as you increase staleness. Put it another way, you actually get more iterations per unit time. That's the left graph here. However, the amount of progress towards convergence you make per iteration decreases due to the error you introduce, and that's the right graph here. The thing is, what we really want is progress per unit time, which is iterations per second times progress per iteration. So it's the product of the two graphs. And we want to find a sweet spot staleness greater than 0 that maximizes progress per second. Conceptually, the graph looks something like this. You push up staleness, you get more iterations per second, but you get less progress per iteration. But the product of the two graphs has a peak somewhere. And that's basically the rationale for using SSP. There is a certain amount of error tolerance you need to give for the system to perform at maximum speed. We also have results for matrix factorization on Netflix and LASSO regression on synthetic data. And in terms of scaling, if we fix the data set, how does SSP perform as we throw more machines at it? So for the New York Times data set, we can show about roughly a 78% speed up for every time we double the machines, and that means you converge in about 0.56 the amount of time every time you double. So it's more or less linear growth. It's not slope 1, but at least it's scaling well up to at least 32 machines which we've tested. We also have some recent results that didn't make it into the paper. Here we're using 8 machines times 16 cores equals 128 threads with 128 gigs of RAM per machine. Now on the New York Times data set, if we increase the topics all the way to 10,000, we can do about 100,000 tokens per second on this cluster. GraphLab does about 80K per second. On the PubMed data set, which is significantly larger at about 7.5 billion tokens, say if we do 100 topics, we get throughput of about 3.3 million tokens per second, and GraphLab gets about 1.8 million per second. We've also been recently using this SSP system, table system, to do network latent space row modeling, large network modeling in the sort of topic model sense. And on a network graph that has about 39 million nodes and 180 million edges, we can do about 50 network rows in about 14 hours versus about 5 days on one machine. And in terms of future work, we actually want to explore in 3 different directions. On the theoretical side, we need to show theoretical results for SSP on MCMC. And we need to do automatic staleness tuning because no one really wants to have to tune these extra tuning parameters. And we'd also like to have some average case analysis to tighten our bounds a bit more. On the system side, we'd like to investigate load balancing to further alleviate straggler problems, fault tolerance, prefetching to improve performance, and other kinds of consistency schemes that are not limited to, say, SSP. But what we really want to do is to enable new applications. We want to enable distributed ML techniques to be applied to hard-to-parallelize ML models, such as deep neural networks, regularized Bayesian methods, and various kinds of network analysis models, all models with a lot of interdependencies between variables and parameters. I'd like to thank my co-authors, James Sipa, Henggang Cui, Jin-Q Kim, Seung-Hak Lee, Philip Gibbons from Intel, Garth Gibson, Greg Ganger, who is not the kid in the picture, and Eric Zing. Right? And I'd like to plug here, we have a workshop demo coming up at the Big Learning Workshop on Monday, where we're going to introduce a system called PETM, which includes the SSP parameter server, as well as a dynamic variable scheduler that's currently under submission. And here we're going to show the sort of results that I've been previewing over the previous slides, topic modeling on 10,000 topics, LASSO regression on 100 billion dimensions, and network modeling on large graphs. With that, I will conclude my summary. Distributed ML is non-trivial. There's a slow network, unequal machine performance. SSP addresses these problems by efficiently using network resources to reduce waiting time. It allows slow machines to catch up. And it's fast like async, but converges like BSP. And the point really is that a parameter server like SSPTable provides an easy interface to quickly convert your single machine parallel ML algorithm into a distributed setting. Slides are available at that link. And with that, that's the end of my talk. Thank you.
And code is also freely available somewhere?
It will be available very soon.
Okay, we have time for one question, I think. Before, meantime, while we take questions, can the spotlight presenters please line up over here if they are not all already ready? Okay, so a single question, somebody must be... Where is he? Here, over here.
So how do you choose S, the number of iterations, sort of where you put the barrier?
Yeah,
And do you know what the optimal S is?
Correct. And so I mentioned that part of future work, we want to do this automatically, but practically what you can do is run for a few iterations, say 10 iterations, and observe the convergence progress of each S. You want to take the one that basically gives you the maximum progress per time. So we're trying to make that automatic in the future version, but for now, the practical thing to do is to just take, say 1 to 2 minutes worth of results and pick the S that does it and do the rest of your 1-hour experiment using that S.
Well, could one also imagine that it's dynamic, that you start out
with
one?
Indeed.
In the beginning, you can tolerate much more.
That is correct.
staleness, but then you have to...
That's also part of our investigation. We do want to have a system where at the start you can tolerate more, at the end you have to use less. In fact, you might even have to become sequential at some point and just tell the threads to line up to actually converge.
Okay, we're going to do one more question. Yes.
Right.
That's actually very close to my question. I'm curious
Right.
how you handle parameters which require like radically different amounts of updates between the steps.
Radically different. So you mean like, say, you've partitioned your data, different threads are going to put different updates.
Yeah.
Well, in that setting, the update is basically 0. So yes, you are committing update, it's just 0.
Let's thank the speaker again.
Mm-hmm.